Hi there. We talked today in class about Rolle's theorem. Rolle's theorem states that if a function is continuous and differentiable on an interval, and if f of a equals f of b, then we can guarantee at least one value in that interval where the derivative at that value is 0. F prime of c equals 0. And so we're looking for those c's, as long as, like I said, those three criteria at the beginning are met. So I've picked two problems here, number 8 and number 14, just to kind of demonstrate the steps and the thought process behind Rolle's theorem. So like I said, Rolle's theorem starts with if f is continuous and differentiable. Okay, so I'm going to evaluate that first, looking at this function. There's no place where the denominator will equal 0. It's not a piecewise, so yes, it is continuous. We're good to keep going. It's not an absolute value, so there won't be a cusp. So yes, it's differentiable, so we're good to keep going. And so then that final step is, does f of a equal f of b? And so I've got my two endpoints here, a and b, and I need to plug them into f to make sure that they are in fact the same, or that they generate the same value. So I'm going to plug in 1, and I'm going to plug in 4. Okay, so when I plug in 1, I get 1 squared, which is 1, minus 5 times 1, so 1 minus 5, which is negative 4, plus 4, which is 0. And when I plug in 4, I get 16 minus 20 plus 4, which is also 0. And so yes, f of a does in fact equal f of b. Okay, so all three of our criteria are met. It is continuous, it is differentiable, and f of a does equal f of b. Therefore, we can find a place where f prime of c equals 0 in that interval. Okay, so I'm going to go ahead and take this derivative, and I'll get 2c minus 5. And I'm going to set that equal to 0. In essence, what we're finding here is a critical number, a potential relative max or min, inside that interval. Right? I'm taking the derivative, setting it equal to 0. Okay, so I can go ahead and add 5 to both sides. We get 2c equals 5. Divide 2, we get 5 halves. Okay, and then you always need to double check because there might be more than one c. You might generate a couple of c's. And so you need to double check that that answer is in fact inside the open interval, meaning we can't include 1 or 4, and we can't include anything outside of that interval altogether, like 6. We can't include 6, right? So 5 halves is 2.5. That is in fact in that interval, and so we're good to go. We've got our answer. Okay, so number 14, which is the other one that I selected here, says f of x equals x squared minus 1 over x on the interval negative 1 to 1. And so same process here. We're going to check first, is it continuous and differentiable? Well, I notice in this particular function I do have a denominator. I have a spot where my denominator might equal 0. So I'm going to say, okay, what value of x would make this denominator equal 0? Well, that value would be 0. So I have a discontinuity at x equals 0. And 0 is on that interval, right? Which means I cannot use Rolle's theorem. Because there is a discontinuity at x equals 0. So that's Rolle's theorem. Again, continuous differentiable, you have to check that. You have to check that the two endpoints generate the same y value, that f of a equals f of b. Then you take the derivative, set it equal to 0, and determine what c's are inside that open interval.